Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
How it was verified? So, Griffith carried out a series of experiments on a glass tubes and the spherical vessel subjected to internal pressure P. These were pre-cracked and then annealed to eliminate residual stresses, if any. And estimated sigma into square root of A as 0.25 to 0.28 MPa square meter. So this is one set of value. He considered that the surface tension of the glass is a linear function of temperature and extrapolated surface tension values of the glass fibers between 1110 degrees centigrade and 745 degrees centigrade to room temperature. And he considered E for a glass is about 62 GPa and surface energy of glass is 0.54 Newton per meter. This analysis gives 0.15 MPa square meter. So this is the right hand side of this expression. So what we have seen in the previous slide is the left hand side of the expression. Though this value is not exactly the same, but there exists a correlation. Correlation between what? What is given, that is surface energy and the crack length. Okay, so the stress required for the incremental crack growth has been established by this equation and also verified by Griffith by some experiments. Though the values are not exactly the same, but there is a good correlation that exists. That means the idea is good to carry it further. So we can now give the definition of the energy release rate, which is G1. That means mode 1. Okay, it's a crack driving force for a mode 1, which is equal to dou UA by dou 2A, which can be written as pi sigma square A by E. Energy release rate is energy released per unit extension of crack front per unit thickness of the body per crack tip. So this is also very important idea. We are looking at energy. Energy per unit thickness of the body per crack tip. So central crack means you have a two tips. So this energy is per tip. Okay, this is very important. Okay, the unit is joules per meter square or Newton per meter, also called as crack driving force per unit extension. And rate has no reference to time in this expression, which normally when we say anything we call it by rate, which involves a time. But here there is no time references there, so it is a misnomer. And we also have another parameter in fracture mechanics called resistance, which is given by R is equal to dou US divided by dou 2A, which is equal to 2 gamma S. Okay. So this is again an inherent property of a material. We have to remember the resistance R is an inherent property of any material which is related to surface energy. So that is how you have to remember now. If you recall, we have already seen that in the earlier classes we derived an expression for the theoretical strength of the a material, right? We looked at some expression for a theoretical strength. That is what we have just found out, and the theoretical strength is always very high as compared to the experimental values, and then we came to an understanding that the dislocations are responsible for this kind of a lower sigma value or yield strength value as compared to theoretical. This is what we have seen in the earlier lectures, right? And what was the, we concluded it is because of dislocation. In this analysis also, Griffith have assumed that flaw, whatever the dislocation we have just assumed in that theoretical evaluation, Here Griffith has assumed that as a flaw size. Okay, the flaw size basically in the brittle material. So he assumed that uh, uh, factor, the dislocation factor here as a flaw here, which is nothing but a crack length in the brittle solid. So why I am saying that here, because where we have looked at the inherent resistance of the material, and which is also related to the flaw inside the material, right? So here also you have a characteristic resistance of each material which is related to surface energy. That is how we will look at it. So G in terms of change in potential energy, this is another important way of representing the G in fracture mechanics. So better to keep a note on that. Consider the case of an incremental increase in the crack area, that is delta A. To cause this crack growth, delta W external is done by the external forces, and the strain energy within the body of the component changes by delta U. Then the available energy G1 times delta A provides the energy balance as follows. So G1A is equal to delta W minus delta U. So this is one of the basic expressions given by the strength of materials concept as well as in fracture mechanics. Okay, so we are trying to look at the delta W minus delta U is also considered as a potential energy, right? So to try to write G in terms of potential energy, this is considered. So dividing the above equation by delta A and taking the limit delta A tends to 0, this is a very important step, and then you get an expression G1 is equal to minus d by dA into U minus W external. Pi, capital Pi is equal to U minus W external is commonly known as potential energy. This is a definition given in the strength of materials. So you just write that expression G1 is equal to minus d pi by dA. Okay, this is in terms of potential energy. This equation is quite powerful to evaluate the energy release rate of a system. G1 is always positive. So remember, this quantity is always positive. G1 is positive for a crack studied for probable growth. So what is delta A? Delta A is nothing but B into delta small a. Okay, where B is thickness of the specimen, delta A is incremental crack length. So it gives a volume. Therefore, the above equation can be written as G1 is equal to minus 1 by B d pi by dA. We can write this expression for a constant load and constant displacement. So we have known this expression before. So you just put that delta pi is equal to minus delta U. For a constant displacement, again we know this expression already, which is delta U. We can write it like this. G1 is equal to 1 by B du by dA, and this is for the constant load for the energy. These are the two energy release rate expression for constant load and constant displacement. So this we have already seen. So just for the recollecting the conceptual idea about how we looked at. So this is just for recollecting why, how we got this expression. So you can look at it again. So you get the strain energy delta U is equal to half E1 dV, and the external work done is again E1 dV, right? So the delta pi is minus delta U. So you can get it like this, and similarly for a constant displacement, again you will see this. A good idea to recall this very nice and important concepts of calculating the strain energy. So we have all this point we have already seen. Just to apply the final expression, and you get the G1 in terms of delta U under the constant displacement. So you get here as delta U is minus of V1 dP, and delta pi is equal to of V dP, which is nothing but delta U. So this is already known. You see, we will also look at this energy release rate by compliance approach. Compliance, why do we do that? Because in fracture mechanics, keeping the mathematics, and not only mathematics but also in experiments, keep it simple, people have recommended compliance approach will be better off. So just to have a idea about what is this. Stiffness of the component decreases with increasing the crack length. This we have seen. Compliance is the inverse of stiffness, K. Okay, this also we know. In fracture mechanics, it is easier to deal with compliance. For a general case of loading, load displacement relation is given by P is equal to K into V. Okay, where P is applied load, K stiffness, and V is the displacement. And the above equation can be written as P is equal to 1 by K times P, or V is equal to C times P. So this is a simple compliance equation, and then we will now use this equation to write this energy release rate. The problem is solved for two extreme cases. One is constant load, in which the displacement of the load point increases as the crack grows, and the another is constant displacement, where the load at the load point decreases as the crack grows. Okay. These two already we have looked at even in the experiment, but in a compliance approach we will write it like this: delta pi is equal to delta U minus delta W external. So we can rewrite these expressions like this, and we know this now. Let me replay this. It is going very fast. So yeah, for delta P, for delta pi, we have this expression, and this is what we are to write, and V can be written like this. So we have to replace dV by this expression. So since it's a constant load, so this term becomes 0, then dV is equal to P dC, and then this is become like this. So delta pi is equal to minus half P squared dC. That is the first idea. So the G1 is written as limit delta tends to 0 minus delta pi by delta A, where delta A is B into dA. So G1 is P square by 2B times dC by dA. So this is a expression for strain energy release rate in terms of compliance. Okay. So for the constant displacement also you should get the same expression, because we have seen that the energy available for the crack extension is the same. So you get this expression again, very simple substitution again. So there it is a dV, here it is a dP. So for a constant displacement, dV is equal to 0. This becomes 0. That means you will get interdependent relation here. Then it becomes C dP is equal to minus P dC, and then you can substitute this dP into this, and then V is equal to Cp. Then you get the same expression: G1 is equal to P squared by dV into dC by d. So this is again reinforcing that experiments like whether it is a constant load or constant displacement, the energy available for the crack extension to grow is the same. Okay, so that is very nice, nicely put forward by this compliance concept as well. So now we'll move to the important concept. I will not go into some other examples now. I will now move on to, okay, we will now get into some new topic involving energy release rate, necessary and sufficient conditions for fracture. What is this? G1 is equal to R1 is a necessary condition. What is R1? It's a resistance of for any given material which is inherent related to surface energy. This is what we have seen. So this is the first condition for the crack to grow. That is, G1 should be equal to R1. It is a necessary condition. For a brittle material, equation 1 is also a sufficient condition. So in the mathematical formulation, we have these kind of conditions. One is necessary condition, another is sufficient condition. And in brittle solids, this equation itself serves as both necessary and service condition for the crack value. We will see how it is demonstrated in the coming slides. For instability occurs when dou G by dou A is equal to dou R by dou A. This is a called sufficient condition. It is not just G1 is equal to R1. Their derivative also should be equal. Then only the fracture instability occurs. So this is called a sufficient condition. Fracture of high strength ductile material is possible only when both the conditions are satisfied. So this is very, very important concept or idea. For a we are going to talk about a stable crack growth and R curve concept. So for that, this particular idea is very, very important. Okay. So the graphical representation of condition of fracture for a brittle material is shown in this slide. So critical stress or a crack length can be determined by this expression, which we have already derived. And for a given stress, fracture occurs when crack length A reaches A critical. This is what the relaxation analogy taught us. Okay, so we will go back to that plot again. We recall that plot. As I mentioned, we will look at this again. So the relaxation analogy has given us a concept of critical crack length, where you can see that. Okay, and now we will extend this idea to a graphical representation again of a condition of fracture for a brittle material. How are we going to actually extend that idea, the critical crack length idea? We are going to now see whether these increase or the crack growth, whether it obeys both necessary condition and sufficient condition and so on. So what is plotted here is energy versus a crack length. This is an actual initial crack length, and this is an incremental crack growth as the crack growth happens. Okay. So what is shown here is energy in the y-axis, and this line is gamma critical, which is R, the resistance. The resistance is plotted here for which is very constant for a given material. So you have this a crack initial flaw in the material of length A1, and then it try to grow. So what does that mean? I mean, when the crack length is A1 and the applied stress is of this much, that means no crack initiation will take place because it is much below the resistance level. So we need to reach G1 is equal to R1. Unless it reaches this point, the crack will not grow. So that is why then only it will satisfy the necessary condition. So that is what is shown here. So now the stress is increased to the next level. Even now the sigma is less than this R, so the fracture does not occur in this region. And the moment you reaches this point, that is sigma C1, that is sigma critical. Okay, fracture initiates from here. That means G1 is becoming equal to R1, the crack initiates from this point. And what you are seeing here is, this is for the constant load and this is for the fixed grip. So what is the difference between these two? So for this, the crack to grow, the energy comes from the external load. But for this, the energy comes within the system, the strain energy within the system. So that you have to remember. The another important point to keep in mind is, you see that as the crack length grows, okay, as the length grows, the energy available for the crack to move is significantly increasing. That means it will propel the crack growth. That means the velocity, the crack growth velocity will be significantly increased. So as it grows, so that is also another important point to keep in mind. Under the fixed grips, energy release rate decreases as the crack length advances. Okay. So for a given crack length A, fracture occurs when sigma reaches sigma C. Longer crack requires less sigma for a fracture. So this is what's shown here. So for a A1, this kind of a stress. For a A2, then again it becomes sigma C. I mean sigma C2, and this is sigma C1. Okay, that's what's shown here. So this is for a fixed grip, and this is for a constant load. For both constant load and fixed grips, the condition for the onset of crack growth is the same. At the point of crack instability, the energy release rate is same in both cases. So this is also true. Point of instability also, the energy release rate is same. So we are now talking about at the initiation point alone. We are not talking anything beyond that. At what stage the crack would initiate. So that is the necessary condition we are discussing. In fixed grips, since external load does not work, the energy release rate decreases as the crack advances. So this is quite obvious. Okay. The energy comes within the system, so it comes down. For further discussion, let us consider the constant load case. The increase of energy availability leads to increase in the crack velocity. I just mentioned in the previous slide. Because as the crack length advances, the energy available is also significantly increasing. Okay, so then that creates or that facilitates the crack velocity. And beyond a certain velocity, crack branching can occur. You see, in the introduction of fracture mechanics slide, I just showed you that in a shadow graph, a crack will accelerate and then it goes and stops beyond the speed, and then it tries to branches, right? So that is also explained by this energy concept. You will see now. I will just recall that plot, just another 2 slides. So what is shown in this plot? This is A dot, that is meter per second, crack growth velocity versus K1, stress intensity factor. So the curve is like going in a shape of a gamma. That's why it is called a gamma curve. You should not confuse this with the surface energy. So what happens is, this is for the amylite 100 material, and what is being estimated here is the start of branching. The crack branching is starting from here, and then it goes up to this point. So the crack branching is experimentally observed, and like I just mentioned in the previous slides, this is shown by Kantoff. So the shadow graph clearly shows that the crack branching is indeed possible, because the crack cannot grow or crack cannot travel beyond Rayleigh wave speed, and then once it reaches a critical speed, it tries to branches out to dissipate the energy, kinetic energy. So how do we support this argument with the energy release rate concept. That's what we are going to see. So energy release rate has given some idea by simple model, a schematic. These are all schematic, but then what you have to appreciate is the conceptual understanding comes better by this kind of schematic. This is an important idea. So we will now look at the simplified model of crack branching based on energy approach. Okay, the crack branching without considering the kinetic energy. Please understand that this is very important, and also we have to remember that this is an infinite plate, and it is the central crack is growing, okay, without any boundary. That is also very important. So it's kind of a fictitious experiment just to appreciate the energy release rate concept. Okay, so now let us see what happens. So now the crack of various crack length A, this is a critical crack length, that is why it is called AC, and this is increments in the crack length and plotted against a resistance R. So the initial crack goes like that, and then you just watch as it just crosses the energy R to 2R, then the crack branching takes place, and then it reaches the 3R, then further crack branches is taking place, and this is happened at a constant load. Okay, so this one contributes to the kinetic energy of crack, and the blue one, the symbolism, note that the height of this line doubles and triples besides the number of crack branches. So it just gives the visual idea or visual impact how it happens. So I'll play this schematic once again. So it is nicely shown that the crack attains a particular velocity, then you try to dissipate the energy like this into branches. So 2R, 3R crack branches. So the bottom line is the energy release rate is able to give some conceptual explanation of crack branching. Okay, that is how we should look at it. So the next idea is Irwin extension of Griffith's analysis. So I just mentioned Irwin extended the analysis of Griffith by introducing gamma p. Okay, so this is what we are going to see, how he has used the same idea of Griffith, and then still he explained the energy concepts for the high strength alloys. Not just Griffith looked at only for brittle solids, but Irwin extended that idea to high strength ductile alloys. In brittle materials, advancing cracks require small energies of the order of surface energy, and therefore once a crack starts advancing, it runs through the body, easily causing catastrophic failure. In most engineering materials, metals and plastic, etc., energy much larger than the surface energy is required to grow a crack. That is quite obvious. Therefore, besides surface energy of the solids, some other mechanisms are operating which involve large amounts of energy. So this is what Irwin started arguing, and English showed that the stresses at the crack tips are quite large. So the large that they cause an elastic deformation, that is plastic deformation is referred here. Okay, this is not anelasticity, which is time dependent deformation. We are not talking here. We are essentially talking about plastic deformation in front of the crack tip. The anelastic or plastic deformation, such as plastic flow in metals, is mostly irreversible, and if the stresses are released, the body will not attain its original configuration near the crack tip. So we are now talking about the plastic zone formation under the crack tip. Okay, the energy that causes the plastic behavior is eventually converted into heat energy and is lost to the surrounding. See, most of the energy or applied stress, okay, involved in deformation goes as a heat. Most of the energy goes as a heat. Only very small amount of energy is being used to actually deform the material, especially in the plastic deformation. So now Irwin has modified this idea, and then he said that in metals, plastic deformation in the vicinity of the crack tip is caused mainly by motion and generation of dislocation, rotation of grains and grain boundaries, formation of voids, etc. All these things we have enough sufficient background to appreciate. And if the material is of low yield stress, the size of the plastic zone is large. So, for example, mild steel. So, the the size of the plastic zone near the crack tip would be very high. A large plastic zone means that a large amount of energy is required to advance the crack tip. That means the plastic zone size is going to now decide the energy required for the crack advancement. Okay, that is a modification by the Irwin. So the overall surface energy can be written as gamma is equal to gamma S plus gamma P. All the other expressions are same, exactly the same similar expressions we can use, but instead of just S, it should be gamma S plus gamma P. Okay, so gamma S surface energy possessed by surface, even it has not been subjected to any plastic deformation. Gamma P surface energy caused by the plastic deformation near the cracked surfaces. So that is how we have to remember this idea. Now we will go to another important concept, the resistance to crack growth in high strength alloys. In a plane strain condition, we are going to see again the same plot, energy versus change in crack length, and this is the crack length is plotted in this side and growth is plotted this side. And in high strength ductile material, resistance to crack growth does not remain constant but increases as the crack grows. So it is not a flat R like we have used in our previous schematic. In a high strength alloys, it grows little bit. So that's why it is just shown in a little curved fashion. So R is increases like this for a high strength alloys. The increase in the resistance is small for the plane strain case. So now that you have to, from now onwards, in fact every concept in fracture mechanics we will look at for a plane stress condition as well as plane strain condition. Okay. Even in the beginning we have just defined this two stress states, right? If you recall the introduction to this course, we have derived a stress tensor for a plane stress and plane strain conditions. So in fracture mechanics, every concept is explained in terms of plane strain and plane strain condition. So this is for resistance to crack growth in high strength alloys. It is like this. So now let me play this. So the moment it reaches the G1 reaches R1, then the crack will initiate, right? Then you will see that is for the constant load type of thing. So this is how the energy versus crack length will appear in a plane strain condition. But in a plane stress condition, the idea is quite different. So the R curve is not that shallow, but here it is quite steep in a plane stress condition. Increase in resistance is very steep. Okay. So the initial crack length, now what happens is, now the crack length A1 with this sigma 1 doesn't start the fracture, and the moment the stress reaches G2, it becomes critical, and then so now we'll stop here and then try to understand this. Stable fracture phenomenon is observed. What is stable fracture phenomenon? So you see, this is a crack length, and initial crack length with the different stresses. The moment it reaches this point, G is equal to R, then fracture initiates. Then after that, the crack started growing. Like if you look at this, the delta A is here. So at this point, if you remove the load, the crack will not grow. The crack will remain in the system without growing. That is why it is called a stable crack growth. We are talking about a stable fracture is here. Okay. So after that, it reaches critical, G critical. Then what happens? Then the catastrophic fracture continues from here. Fracture initiates at sigma 2, stable still just below GC. Beyond GC, it is unstable. So below GC, at any point, if you remove the load, the structure will not collapse or the crack will not grow. That is why it is called a stable fracture. After GC, it becomes unstable fracture. So crack extends from A1 to A1 plus delta A1 by stable fracture. At GC, G1 is equal to R1 and dou G1 by dou A is equal to dou R1 by dou A. So here you see it's very interesting. We are not only satisfying the necessary condition but also a sufficient condition. Okay, so which explains the stable crack growth behavior in the plane stress conditions of high strength alloys. So here the energy release rate concept is very useful in realizing the stable crack growth phenomenon. Very, very important idea to remember. Sigma C is not fracture strength at crack length A1 plus delta A1, but A1. So this is something, this is always a critical crack length, but it is not, we should not consider delta A1. So A1 remains always a critical crack length, but this is, you should not add this. That is the caution here. This is a serious error, normally reported in the fracture mechanics calculations and misinterpretation and so on. You see, for a plane stress condition, if the G varies linearly with the crack length, the condition dou G1 by dou A leads to a contradiction, because if you keep on adding different crack length, when you look at this idea, A1 reaches a critical value, then as for a different crack length, it goes and meets at a different position. And this is not going to be true, because the G should be the same for any crack length. That is why this kind of analysis is going to have a problem. Okay, so then what is the remedy? What is the remedy? Remedy is we have to consider something called A by W. So what is A by W? See, in these previous experiments, we considered the crack in the infinite plate, and there is no, boundary. Okay, so the moment you bring in that boundary, that is width of the specimen, then that is being corrected. So in this case, you can see that for a finite panels, G1 lines are curved. In the infinite panel, the line goes and make an intercept or make a tangent at a different point. But for a finite panels, then you bring a parameter called beta, which is function of A by W. Then G is not just a straight line, it is a curved line. So for example, if you take A3, for a crack A3, the G is GA here. It meets the GA here. For a crack length A4, the G is GB here. So G and GB are almost very close. So this takes care of that problem. You bring in a beta, which is a function of A by W. Okay. So this leads to approximately the same GC for all the crack lengths, and this is in agreement with the critical fracture toughness KC obtained based on the stress criteria. Okay. So what we have understood from this today's lecture is energy release rate is a significant, made a significant improvement in understanding the crack problems, and it also explained, the concept of critical crack length, and it explains the stable crack growth, and it paved the way, for the further understanding of the fracture mechanics problems. Okay, so without getting into much of a mathematics, simply using this concept of energy, a lot of understanding has come from the complicated crack problems. Okay, so with this we will kind of finish this discussion on energy release rate. In the next class we will start discussing about the stress fields and the displacement fields. Okay, I will stop here. We will continue in the next class. Thank you.